Hello, good afternoon, everyone. So, hope I am audible to you.
Yeah, yes, you are.
Yeah. On behalf of ITMAS, I would like to welcome you all to this workshop, Beyond the Scoreboard, Data Driven Cricket, Decoding the Game Through Data and Probability. So, in this workshop, we'll be exploring on how statistical methods are used to analyze cricket performance and strategies. So, let's move on. So, yeah, these are the topics which we'll be going to cover in this workshop. So, part one is the foundation, introduction to cricket analytics, case study, the 2008 IPL value model, batting metrics, average versus strike rate. Then comes data visualization, quadrant analysis, and last, bowling metrics, pressure and lethality. And part two is strategy and probability, where we cover the subtopics, the run rate delta, CRR versus RRR, the geometry of field restrictions, the matchup metrics, conditional probability, Win-Wiz, Bernoulli trials and probability curves, the final over case study, the digital toolkit and the future of ML, Duckworth Lewis Stone, that is DLS method. So, yeah. So, what is cricket analytics? So, it is the application of statistical methods to evaluate player performance and match trends. So, cricket analytics means using data and statistics to analyze or to understand cricket better. Earlier, as we know, most of the decisions were based on experience or intuition. But now teams use numbers and data to make smarter decisions. So, for example, if I have to say which bowler performs best in death overs, or which batter struggles against spin, which field placement works best against a particular player. So, here instead of guessing, teams are using data to make evidence based decisions. And the second point is the data point. So, in cricket analytics, every single ball or every single delivery is treated as a data point. That means what? Every delivery gives us a useful information. So, over a match, this becomes hundreds of data points, and across a tournament, this becomes thousands of data points. So, this helps the analysts to identify the patterns, strengths of the batter, bowler, weaknesses of them, the trends. For example, if I have to say if a batter gets out frequently to short balls, so analysts will identify this pattern. So they will understand their strength and weakness. They'll understand their weakness here. So each ball is recorded with variables like outcome, speed, line and length, and batter position, where outcome is the either the number of runs they scored or the dot balls, wickets taken, boundary or six. The outcome may be any of this. So, example, if a batter scores many boundaries against fast bowling, that becomes a strength against fast bowling. And if talking about speed, this records how fast the ball was bowled. That means the pace of the delivery. So, for example, if I have to say some batters struggle against high pace, while others struggle against slow deliveries. So, teams use this to basically decide which bowler to use and when to bowl them. The third point is line and length. So this records where the ball was pitched and directed towards. So if a batter struggles against full length balls outside off stump, bowlers will target from the next match onwards, they'll target that area. So this helps them plan bowling strategies. And the last point, batter position, this tracks where the batter is standing or moving. So if a batter moves across the stumps often, bowlers might bowl wide outside off stump. So this helps in predicting batter behavior. So our main objective here is that we are moving from descriptive, that is what will happen, to predictive. Sorry, what happened, to predictive analysis, that is what will happen. So if, for example, if I have to say let's say a batter scored 50 runs in a match. So that is what we already know. So that is what has already happened. So we go from descriptive to what will happen. That is predictive. We'll analyze the data and we'll understand that this batter might struggle against spin in the middle overs. So that is predictive analysis basically. So this based on past data, we analyze this. So teams basically use this information to plan bowling, set the field, choose players, etc. Moving on to the next slide, we have this case study, that is value over stars 2008 IPL victory. So as we all know, IPL started in the year 2008, and Rajasthan Royals actually won the first IPL season, which is on 2008, despite having a very low budget and a very few star players. So from this, what we understand, it was under the captaincy of, it was a very brilliant captaincy, we can say, it was under the captaincy of Shane Warne. So they focused on underrated players like Yusuf Pathan, Shane Watson, Graham Smith. So these players, basically, those people were not considered big stars then, but they performed exceptionally well. So that is the main point here. So the main observation the team did was that they focused on undervalued players or consistent players, and as a result they got a very strong performance at a very lower cost, and what, they won the IPL title. So this is a classic example of analytical thinking, that is finding value over stars instead of relying on subjective judgment, that is focusing on the stars. These people, what they did, they relied on the objective decision making. uh, they found the value in the players and they just chose those kind of players, and that's how they won the match. So the connection with modern analytics. So today, what happens is that today teams use Z-score to identify such hidden performers. Where Z-score formula, we all know the Z distribution formula, which is given by Z is equal to X minus mu divided by sigma, where X is equal to the player's performance, mu is equal to league's average performance, and sigma is equal to standard deviation of league's performance. So what we can understand, what it shows is basically higher the Z score, player performance is above average. So it helps us find undervalued but high performing players. So Z score tells us how better or worse a player is compared to the average. So if I have to say an example, let's say the average runs of the team is like 30 and the players runs is 45. So basically what it means, 45 is greater than 30. So that means his Z score is positive. So he's having more than the average runs. So his Z score is positive. So he's a above average player, we can say. So so they use set score to find underrated players or identify consistent performers, and thereby build strong teams. So in this slide, we can actually see the bell curve of the 2008 Rajasthan Royals team members. The players like Shane Watson, Graham Smith, and Yusuf Pathan, who were identified to be the hidden gems, those players have been denoted here in this bell curve. So as you can see, the middle region of the bell curve represents the average players. So these players perform around the league average, and towards the left side, we can see the below average players who had a negative Z score. And yes, towards the right side, we can see the above average players. So Shane Watson had a pretty good Z score. That is, his Z score was around 2.4 sigma. Graham Smith at the same time had a Z score of 1.9 sigma, and Yusuf Pathan similarly 1.6 sigma. So these people were having +1 sigma score. So here to the left side, you can see how to calculate Z scores. Z is equal to X minus mu by sigma. So if a player has a strike rate of 133 and his league average is 120, and the league average is 120 and standard deviation is 10, then Z score can be calculated as 130 minus 120 divided by 10, which is 1.3, 1.3 sigma. So that's how we calculate Z score. And at the rightmost end, you can see Sachin Tendulkar. He was having a Z score of more than 2.5 sigma. So that's why he is categorized as overvalued star. We all know his price was very high. He was a very expensive player. And yeah, that's it about this bell curve. So these players were identified to be the undervalued players back then because those people were not stars back then. Later, eventually, they became stars. So yeah, this is an analysis of 2008 hidden gems team. Moving on to the next slide. Batting average versus strike rate. So we come to the metrics of cricket. So we can see batting average. As we can see, it measures reliability and consistency. So we have the formula: batting average is equal to total runs divided by dismissals. So it shows us how many runs a batter scores before getting out. So higher the average, that means a player is dependable. So if, for example, we have to say Virat Kohli has a very high average, so he's a very reliable or a very consistent player. If to take an international player, we can say Kane Williamson is known for his consistency. So basically, batting average tells us how dependable a batter or a player is. And next comes the strike rate. So strike rate measures how fast a batter scores runs. For batting average, when it was total runs in terms of dismissals, here we have how fast the batter scores the runs. So the formula is strike rate is equal to runs divided by balls into 100. So it measures the scoring speed. And if I have to say an example, then if a player scores 30 runs in 20 balls, then his strike rate will be, so his or her strike rate will be 30 divided by 20 into 100, which is equal to 150. So here, see, when the strike rate is 150, that is equal to, that means what? 1.5 runs per ball. So here, that is basically his strike rate. So this is important in limited overs cricket. Why we say that? Because strike in limited overs cricket, we don't have much time in the crease, so in the ground. When it comes to death overs, the last 4 or 5 overs, the strike rate is much more important than the batting average because we just have very few overs or very few balls. So in that, we'll have to score more. So yeah, so player strike rate of above like 150 plus means he's a very aggressive batter. Strike rate between 120 and 140 is considered to be a balanced score, and strike rate below 100 is slow scoring actually. So, example, Glenn Maxwell is a fast scoring uh, batter, or AB de Villiers. Say if all these players are having a high strike rate. So, yeah, so a good team basically needs both. A good cricket team basically needs both players who are both reliable and at the same time who score quickly. That is, who are both dependable, who has a good batting average and a good strike rate. So these players we can see in the next coming slides. We can see that those players are called as allied players. So yeah, moving on to the next slide. I have a very simple question. You guys can answer if you want in the chat box. So a batter scores 8 runs in first 10 balls, then 22 runs in the next 8 balls. So was the slow start harmful to the team? It's just a yes or no question. Maybe you can answer yes or no if you want to. And yeah, that is the question. A batter scores 8 runs in the first 10 balls, then 22 runs in the next 8 balls. So was a slow start. Slow start here means 8 runs in the first 10 balls, harmful to the team. You may answer either yes or no in the chat box. Yeah, exactly. It's no, because yeah. So we can say that not necessarily, right? Because why? Because the bat initially, though he scored only 8 runs in the first 10 balls, then 20, he scored 22 runs in the next 8 balls, which means that his strike rate improved. So the match, basically here the match situation matters. So batter accelerated later. If he was scoring at the same rate throughout the match, then it would be bad for the team. But since later on the strike rate increased, he scored 22 in just 8 balls. It is pretty good. So it's not necessarily harmful to the team, we can say. So the trade-off. In cricket, there is often a trade off between batting average and strike rate. So, you know, higher the average, that means safer batting. So it denotes what? Lower strike rate. It can be lower strike rate. So higher average when it's safe batting, the strike rate might be low because he may be in the balls might be uh, more. So since we are calculating strike rate in terms of number of balls, the strike rate can be low when the average is high. And the next is if higher is the strike rate, then it will be aggressive batting, and lower will might be the average. So basically, teams look for elite players who maintain both high average and high strike rate. So the math insight. So let's say player A has scored 40 runs in 40 balls. So his strike rate will be, as we saw in the formula, 40 divided by 40 uh, into 100. So it's 100. And he uses 33 percentage of team's balls in T20 format. If to say in T20, because we have one total of 120 balls in T20. So when he uses 40 balls, it's 33 percentage of team's balls. If you have to say about player B, then he scores 20 runs in just 10 balls. So his strike rate is 20 divided by 10 into 100, which is 200. So he uses only 8 percentage of the balls. So what can we understand? The math insight here is that player B scores quickly and leaves more balls for the teammates, for the remaining people, remaining batsmen. This helps the team reach a higher final score later on. So that's what it. Even though the player A, he scores 40 runs. Since he uses 33 percentage of the balls, but the player B has a more strike rate and only uses 8 percentage of the ball. Player B is actually contributing much here because he leaves more balls for the teammates so that they can reach a higher final score later. They have more balls remaining. Yeah. So here comes the batting performance quadrant analysis, which okay, so here we can see quadrant one, uh, which has the elite players, quadrant two, which has the finishers, quadrant three, which has the underperformers, and quadrant four, which has the anchors. So here, as we can see, in quadrant one comes the players who are having both high, as I have mentioned before, are having both high batting average and high strike rate. So let's see. Here we have player A with a good batting average of 48 and good strike rate of 160. And player G also has a batting average of 39 and a strike rate of 158. So next comes quadrant two with the so-called finishers, the people who are having good strike rate but very low batting average. Here we can see player C is having a batting average of 29 and strike rate of 166, and player F is having a batting average of 24 and strike rate of 155. So they are basically called finishers because they come towards the end, maybe towards the death overs, and then they, you know, uh, score very high runs. So that's why they have a higher strike rate, but their batting average is low. Yeah, coming to the um, third quadrant, we have player D with a low batting average of 34 and low strike rate of 135, and player H with a low batting average of 31 and a strike rate of 134, and player I with a low batting average of 27 and strike rate of 129. Next comes the anchors who are in quadrant 4 having high batting average, but their strike rate will be low. So these players are, as I said, anchors are the players who are having high batting average, so they'll be more dependable players. So as you can see, player B has a batting average of 42 and strike rate of 130, and player E is having a batting average of 51 with strike rate 130. So this is basically the quadrant analysis where we can see all different uh, players distributed in different quadrants based on their batting average and strike rate. So yeah, this is an interactive activity where maybe you can answer. So imagine the scenario where you are the captain of your team and your team needs 30 runs in the last 2 overs. So you have to choose one batter. So you have KL Rahul as your first player with an average of 46 runs and a strike rate of 139. And you have player B as Hardik Pandya with an average of 29 and a strike rate of 152. So who would you pick for the last 2 overs? Um, like imagine you are the captain of your team. So who will be your choice for the last 2 overs? Y- Yeah, it is Hardik Pandya. So he'll be the better choice. Yeah. So you are right, it's Hardik Pandya because his strike rate of apparently his strike rate is 152, which is a high strike rate compared to KL Rahul with a strike rate of 139. So since last 2 overs means we know those are the death overs. So choosing a person with high strike rate is good. So yeah, moving on to the next slide. So now comes the bowling metrics. Uh, so the first metrics that we are going to learn about is economy rate. So economy rate has the formula. Economy rate is equal to runs conceded divided by overs bowled. So so this measures how many runs a bowler gives per over. So it tells us that how much pressure the bowler creates on the batter. So lower economy rate means more pressure on the batters. So if I have to say an example, if a bowler gives 24 runs in 4 overs, so his economy rate will be what? 24 divided by 4, which is equal to 6. So this means that he gives 6 runs per over. He just gives 6 runs per over, which is considered to be good economy rate. So, if to say an example, we have players like Jasprit Bumrah. We all know that he's known for his good, low economy, and other bowlers like Ravindra Jadeja. Maybe he builds pressure with tight bowling. So these are all the players with low economy rate. So they build more pressure on the batters. And next comes a bowling average. So bowling average is it measures the lethality. So lethality here means how quickly a bowler takes wickets. So that's why the formula we have here, bowling average is equal to runs conceded divided by wickets taken. So it measures lethality. That means how quickly a bowler takes wickets. So lower the average, more wickets are taken. So if to say an example, if a bowler gives 50 runs and takes 2 wickets, so his bowling average is 50 divided by 2, which is equal to 25. So this means that the bowler takes 1 wicket every 25 runs. So we can say that if the bowling average is below 20, then it's considered to be pretty good bowling average, and if it's 20 to 25, it's fine, decent bowling average. And if it's 25 to 20, 30, then it's average, or above 30 is less effective. Since we are considering it in terms of wickets, the less number of wickets taken, then the more will be the bowling average. So that will be less effective. So players with low bowling average, we can say Mohammad Shami, and the former player Anil Kumble, he was known for taking wickets regularly. So those are the examples of bowling average. So basically, a best bowler is a person who can control the runs and take wickets both at the same time. So that means both with the lower economy rate and lower average. So next comes the dot ball probability. So dot ball, as we all know, is a ball where no runs are actually scored. So dot ball probability tells us how often a bowler prevents runs. So if a bowler bowls, example, if a bowler bowls 24 balls and 12 are dot balls, then P of dot is equal to 12 divided by 24, which gives us 0.5, or that means what? 50 percentage. So this means that 50 percentage of the balls ball gave no runs. This basically is creating pressure on the batting team, because 50% of the balls balled were having, like, they did not score any runs. So if so, the inverse relationship here is as P of dot, that is, as the number of dot balls increases, scoring decreases, right? The runs, the number of runs scored are decreased. So that is an inverse relationship. So as a result, the required run rate for the opponent increases exponentially. So if the batters face many dot balls early, they must score much faster later. So the required run rate, that's why it said that the required run rate increases quickly later. So they'll have to balance, they'll have to chase the targets. Of course, their required run rate will increase. So this is another question which you can answer. A bowler bowls 4 overs and concedes 52 runs, taking 2 wickets. So calculate his economy rate and bowling average. If you want me to proceed with the answer, I'll move on. Okay. So as you can see, the economy rate is since the runs conceded are 52, so economy rate will be 52 divided by the total overs. So 4 overs, he balled 4 overs. So 52 divided by 4, which gives us 13. So which means that he is conceding 13 runs per over, which is considered to be extremely expensive. That means he's giving too many runs. 13 runs per over. So which is expensive. That is, he's giving too many runs. So next comes the bowling average, which is equal to 52 divided by 2. That is the number of wickets taken. So 52 divided by 2 gives us 26, which means that he takes a wicket every 26 runs. So it is reasonable at the death overs, but the economy makes him a risk. So this means that bowler gets a wicket after conceding 26 runs. This is not bad in when it comes to death overs, because we all know that death overs are the last 4 or 5 overs of a match. So batters attack more, and then because of that they usually score more runs towards the end. So average of 26 is fine, it's acceptable. But the economy rate, his economy is like 13 runs per over. So uh, which makes him which makes his economy risk. So even though he takes wickets, he is giving too many runs. So the bowling team may lose match because the batting team is scoring high. So we can say that here the wicket taking is good wicket, like he's having a pretty good bowling average, but because of his poor economy, the bowler is considered to be a risky bowler. So this bowler takes wickets but also gives too many runs. So while he is useful for breakthroughs, his economy makes him risky in tight matches. So next comes the run rate delta, that is CRR versus RRR. So here CRR is current run rate. So current run rate is nothing but runs scored divided by overs ball. So this basically measures the actual scoring pace. It tells us how fast the batting team is currently scoring. And in, so if, for example, if you have to say if a team scores 80 runs in 10 overs, then the current run rate is 80 divided by 10, which is 8 runs per over. So RRR reflects actual scoring pace. And when it comes to required run rate, it is equal to runs remaining divided by overs remaining. So it reflects pressure and future demand. As in, for example, if a team needs 100 runs in the remaining 10 overs, then the required run rate will be 100 divided by 10, which is equal to 10 runs per over. So now we compare, here we have delta RR, which means run rate delta is equal to CRR minus RRR. So this means that negative delta, that is if required run rate is greater than current run rate, that means the batting team is behind. So bowling team is right now in control. And if it's zero delta, that is if current run rate is equal to required run rate, this shows that the match is perfectly in level. That means the required run rate and current run rate is equal. So if it's positive delta, that means if the current run rate is greater than the required run rate, then batting team is ahead. So basically that means that they are chasing comfortably. So here this graph shows us a yellow line and a red line, where a red line shows a required run rate and yellow line shows us current run rate. So we can see this is a T20 chase. So as the match progresses, we can see the required run rate increasing. So basically, if the required run rate is increasing, the pressure is building, and it means what? Batters must take more risks. So this is a live chase breakdown of a T20 chase. As you can see, the scenario is that the target is 190 and it's T20. So we have 20 overs. So in the first 6 overs, the runs scored were in the power play. Basically, the runs scored were 52. We have total of 52 runs, and The current run rate is 8.67, which is 52 divided by 6, and the runs remaining is 138, as you can see, and we have the required run rate is 9.86, which is higher. As you can see, it's higher than the current run rate, so we have a delta of negative 1.19. So slightly there's a pressure, but it's fine. Eventually, if they are able to make it up, it's fine. And next, in the 10th over, that is between 6 and 10 over, they are scoring, the run scored is 38 runs. So they have a total of 90. And yeah, their current run rate is 9, and runs remaining is 100. Required run rate is 10 now. So it's the delta slightly decreased and it became -1. But still, there's a bit of pressure since its current run rate is not equal to the required run rate. Now, between 10th and 14th over, they scored 42 runs, and the total is 132 now. Current run rate is 9.43, and runs remaining is 48. Uh, okay, runs remaining is 58, and required run rate is 9.67. So now their delta is again decreasing. It decreased to 0.24, negative 0.24. That means they are closing and they are reaching to zero, towards zero, right? So yeah, now the pressure is decreasing. And between 14 and 17th over, you can see the run scored is 28 runs and total is 160. And current run rate is 9.41, runs remaining is 30, and required run rate became 10. So here there is a slight increase again. So from 0.24, instead of decreasing, it became negative 0.59 and increased. And in between 17th and 19th over, the run scored were 22. Total has become 182, and current run rate is 9.58. Runs remaining is just 8 runs, and required run rate becomes 8. So here now we can see it became, the current run rate is now more than the required run rate. So of course we'll get a positive value, and now it became plus 1.58. That means that batting team is ahead now. So um, so what now? There's no pressure. They are batting comfortably. So in the last over, that is in the 20th over, the runs they scored were 8. So total runs became 190. That means they reached their target. The current run rate became 9.5, and the runs remaining is 0 runs. That means required run rate is 0. So finally they won the match. So by tracking CRR and RR, we can predict match momentum mathematically. So this is how modern cricket analytics works. So yeah, and just whatever I mentioned here before is written here in this slide. At over 6, delta is minus 1.19. Batting team already under pressure despite decent power play, but that's fine. At over 14, delta narrows to negative 0.24. So game is almost level, momentum shifting. So what it means the delta is at over 14, delta is negative 0.24, which is very close to 0. This means the batting team is almost matching the required pace. So pressure is reducing, match match is becoming balanced. So and at over 14, delta drops to negative 0.59. A wicket here could have ended the chase. That means delta becomes more negative. So negative again. So required run rate increase slightly. Batting team is again under pressure. So at over 17, pressure builds again. The batting team is slightly behind the required pace. If a wicket fell here, the chase could have become very difficult. But since it didn't, it's fine. So at over 19, the delta flips back to plus 1.58. Batting team now is in full control. So the swing from negative to positive delta is actually called as a momentum crossover point. So the key takeaway here is that the delta didn't flip until over 19. Means the bowling team was in control for till 19th over. The bowling team was actually in control of 20 overs, but yet still they lost the match. Still the bowling team lost the match, right? This shows that how one one over can, statistically redefine an entire match. So, so in T20 cricket, momentum can change at any moment, and mathematics help us predict that shift. So even if a team is in control for most of the match, one strong finish can completely change the result. So in the last one over, that's how finally they won the match. So yeah. So there's another question which you can answer. A team needs 75 runs in 6 overs. So after 3 overs, they have scored 28. So what is their new run rate? Uh, and has the pressure increased? You may answer any one of these, or like if the pressure has increased or not. Yeah, so clearly it's 15.6. That means the pressure has increased. So yeah, as we can see here, runs remaining was 75 minus 28, which is equal to 47. So overs remaining was 6 minus 3, 6 minus 3, which is 3. So new run rate becomes 47 divided by 3, which is equal to 15.6. So original run rate was 75 divided by 6, which is equal to 12.5. Now it shifted. See, the pressure has increased. We can see it here. New run rate became 15.67 and the previous one was 12.5. So the pressure has increased by 3.17 runs per over in just 3 overs. So, and required run rate of 15.67 is a very high required run rate, and significantly it increases the pressure. So this chase is now in a serious phase. So that means what? One slow phase is essentially decided the match. So at last, at the remaining 3 overs is decided. Like now it becomes kind of, since the pressure has increased, it becomes a bit difficult for the batting team to score since the required run rate is high here. So yes, that's it from my side.
Uh, you can stop presenting. Am I audible? And you guys can see the presentation, right?
Yes, yes.
Yeah. So, all right, everyone. Now we are stepping into one of the most intuitive yet mathematically deep topics in all of cricket analytics. It's the geometry of where fielders stand and why they stand there and what the data says about where they should stand. This entire topic is built around one central structural feature of the game. It's the 30-yard circle. Imagine you are standing right at the center of a cricket ground, right at the pitch. Now, mentally draw a large circle around yourself with a radius of 30 yards. That is approximately 27 meters. This is the fielding circle. This divides the entire cricket field into two distinct zones. Now, in T20 cricket, the laws of the game impose very specific restrictions on how many fielders should play outside this specific circle. And these restrictions completely change the mathematics of the game. The first one is the power play overs, that is from overs 1 through 6. During this phase, only two fielders are allowed outside the 30-yard circle. Think about that. In a full fielding side of 11 players, only two of them can patrol the boundary during the first 6 overs. Everyone else must be inside or on the circle. This is why you see so many boundaries in the power play. The outfield is essentially unguarded. And then comes the middle overs, that is from overs 7 through 15. This restriction relaxes significantly here. Now, up to five fielders can be placed outside the circle. The captain suddenly has far more flexibility to plug gaps and set defensive fields. And the final phase is the death overs, that is from over 16 through 20. Uh, it represents the phase of a T20 match with the highest analytics usage for delivery selection. Uh, Basically, the death overs have the highest analytics driven delivery selection phase. And because the marginal value of every analytically informed decision, it is at its absolute peak when the game is on the line and every run counts in the death overs. And so now the big question is within these restrictions, where do you actually put your fielders and how do you decide? And this is where short distribution data comes into picture. Cricket analysts have compiled data from thousands and thousands of T20 power play deliveries. Specifically, here we'll look at right-handed aggressive opening batters mapped with every boundary scoring shot went. They built what is called a short distribution map, essentially a heat map of boundary probability across every zone of the cricket field. And here is what the data shows. The cover region accounts for 28% of all boundary probability. This is by far the highest zone on the field, and it makes sense once you think about it. The cover drive is the most naturally grooved shot for most right-handed batters because when a ball is bowled in full and slightly outside off stump, the cover drive is the instinctive high percentage response. During the power play with only two fielders outside the circle, there is almost nobody covering covering deep cover. It is a massive open scoring zone. And then after cover region, then comes the square leg. The square leg region accounts for 19% of boundary probability. Uh, and the right-handed batters will pull, flick, and sweep through square leg regularly, particularly against anything short or angled into their body. And then the point region, backward of square on the offside. It accounts for 14%, and the mid-off region accounts for 15%, and the fine leg region accounts for 12%, and everything else like miscellaneous shots, top edges, and unusual placements accounts for the remaining 12%. And now let us run the actual numbers and see why this matters so much. Uh, if you are a data-driven captain and you place your two outside fielders at cover and square leg, now you are blocking 28 plus 19% of boundary probability. That is 47% of all boundary risk covered by just two fielders. But uh, but if you are a traditional captain, I mean traditional minded captain, you will rely on gut feel. You place your two outside fielders at the fine leg and mid on because that is the standard conventional defensive positions that have been used for decades. Fine leg covers 12% and mid on covers 15% for this specific batter. Combined, that is 22% of boundary probability protected. And the gap between these two approaches is 25 percentage points of boundary protection from the exact same number of fielders. And that is an extraordinary competitive advantage, and it is available to any team willing to invest in collecting and analyzing short distribution data. And that is what mentioned in this slide. And then the power play optimization. 1 minute. Hello, am I audible? Guys, can you hear me?
Yes, yes.
Now let us look at three power play bowling strategies that have been compared across all data sets. Uh, the first strategy is the pace heavy attack. This is the traditional approach. You bring on your two fastest bowlers, you bowl hard lengths, try to generate pace and bounce, and try to beat the batter through raw speed. It looks aggressive and it feels right, and the crowds love pace. But what does the data show here? Average runs considered is 54, and the average wickets taken is 1.8, and the dot ball percentage is 31%. And the second strategy is spin only. This sounds completely counterintuitive. Most people won't agree with spin during power play overs. But the data here shows the average runs considered is 48, which is the least among the other two. That is significantly lower than pace, and the average ticket wickets taken is 1.4, which is also lower than pace. The dot ball percentage climbs to 38, 38%, which is higher than pace. So spin is more economical and generates more dot balls, but takes fewer wickets. And the third strategy is mixed. It is a data-driven approach. Here, one pace bowler and one spinner or specific sequencing of bowlers types based on matchup data will be introduced, and they are selected analytically for each over based on which batter is facing. And the result will be the average runs considered is 49 and almost as good as spin only. Average wickets taken is 2.1, better than both other strategies. And the dot ball percentage is 36%, which is between pace heavy and spin only. So the mixed strategy wins on the most important single metric, the wickets taken, while keeping runs considered nearly as low as the spin only approach. But here is what makes this so striking. Most teams go with pace in the power play because that's what has always been done. That's what feels right to them. And that's what the crowd loves too. This is exactly the gap that analytically driven teams are quietly exploiting every season. And here's a small question for you guys. From what we have seen in the last previous slides, which phase of a T20 match has the highest analytics usage for delivery selection? Mm. So it's the death overs. And the next question is, traditional captains place fielders at fine leg and mid on during power play. Based on the short data above, what percentage of boundary probabilities does that protect from this data, guys? Fine leg and mid on. So it covers 22%. And the next topic is the matchup matrix conditional probability. Now we are going to move into one of the most mathematically rich concepts in the entire presentation, the matchup matrix, and the statistical framework behind it is the conditional probability. The formal definition from probability theory for conditional probability is the conditional probability of event A given that event B has already occurred is written as P of A given B. The formula is P of A given B equals P of A intersection B divided by P of B. This means that given that a specific situation has already occurred, what is the probability that a specific outcome follows. In cricket, we apply this to the bowler versus batter matchup, specifically probability of wicket given bowler versus batter type, which means given that a particular type of bowler is bowling to a particular type of batter, what is the historical probability based on thousands of past deliveries that wicket falls on any given ball. So from this matrix, we can see right arm fast bowling against a right-hander top order batsman produces a wicket probability of 8.2%, and against a left-hand top order batsman, oh what? Yeah, this one. Uh, right hand lower order. Oh, okay. We can go with this scenario here. The scenario here is we are in the 17th over, and the batsman is a right-hand lower order batsman, and the team needs wickets right now. We have four bowlers who have overs pending, and the type is right arm fast bowler. He has a wicket probability of 7.8% against this specific batter, and his dot ball percentage is 29%, and his economy is 8.2, and his best delivery is Yorker, and the boundary rate is 28%. And the bowler B is a left arm fast bowler. His wicket probability rises to 9.2%, better than bowler A, and the economy rate is 7.8, and his best delivery is in swinger, and the boundary percentage is 24%. And for bowler C, he's a off spin bowler, and his wicket taking probability is 12.4%, and the dot ball rate is 41%, and his economy is 6.9. His best delivery is on ball, and his boundary chance is 18%. And for bowler D, he's a leg spinner, and his wicket taking probability is 11%, and the dot ball percentage is 38%, and economy is 7.4%, 7.4, and best delivery is googly, and his boundary rate is 21%. And now let us apply the multivariable decision framework, going through it step by step. Step one, our first priority is wicket taking. So you need a wicket because a wicket right now essentially ends the threat. Which bowler has the highest wicket taking probability against this batter from this matrix? Uh, the bowler C, off spinner. He has a wicket taking probability of 12.4%. And then the step two, economy priority. You need to contain runs regardless of whether you take a wicket, because every run the opposition scores changes the required run rate for your team. Which bowler has the lowest economy rate here? It's still the bowler C. He has the lowest economy with a economy of a 6.9. And then the step three, dot ball priority. You want to build psychological pressure through dot balls, forcing the batter into an error through accumulated frustration. So which bowler has the highest chance here? It's still the bowler C, off spinner. So off spin wins on all three matrices against this specific batter type. This matchup insight is completely invisible without data. So you cannot see it by just watching matches, because the sample size in any single match is too small. You cannot feel it through intuition also. The only way to discover it is through systematic analysis of thousands of historical ball by ball records. And once you know it, once your analytics team has run this matrix for every batter in the tournament, you have a real usable edge. And this is exactly why top T20 franchises make unconventional bowling changes in the death overs. Um, when a captain brings on a spinner in over 17th with a match in the balance, and what they're often really seeing is a captain who trusts in his analytics over his instinct. So the key takeaway here is the uh, bowling selection matrix removes bias, and it removes the conventional instinct, and it replaces both with probability. and then the Bernoulli trials and probability curves. Um, a Bernoulli trial is a random experiment with exactly two possible outcomes, uh, like success or failure, or one or zero, maybe yes or no, like that. It will have binary outcome. And in cricket analytics, we model each individual delivery as a Bernoulli trial. The binary question here is, did the batting team advance their winning position on this delivery, or did they lose ground? And now the key mathematical framework that builds on Bernoulli trials in cricket is the winning probability model. And it is expressed as the probability of win is equals a function of runs required, wickets in hand, and overs remaining. And this is a dynamic Bayesian update, meaning after every single ball, the model receives new information, what happened on the delivery, and updates its probability estimate for both teams. And Bayesian inference starts with a prior belief that your best estimate before seeing any new evidence, like at the start of the game. Uh, at the start of a T20 chase with no balls bowled, and uh, the priority might be roughly 50-50 for both teams, but adjusted slightly based on team strength and historical head-to-head data. Then new evidence arrives, maybe ball one, maybe the batter hits a boundary, the model updates. It now estimates that the batting team's win probability has increased slightly, maybe from 50% to 53%, because they have scored 4 runs faster than required. This process happens after every single delivery throughout the entire match. Each ball is a Bernoulli trial feeding the Bayesian update, and the output is a live, continuous, updating winning probability curve for both teams. The lines you see moving up and down on a broadcast graphics throughout a match. Um, Looking at the live win probability here, you can see Team A's win probability starting at 50%, rising through the power play to around 70% as they build a strong position, then gradually declining through the middle overs as Team B starts to find as Team B starts to get comfortable and crossing over around 13 over 13 here, where both teams are approximately equal, and then Team B's probability rising sharply through the death overs as they execute a successful chase here. This crossover point is called the momentum crossover point we discussed earlier, and you can see graphically plotted with mathematical precision here. Now, think about the enormous amount of historical data that has to underpin this model for it to be accurate. The win probability model has to know for every combination of runs required, wickets in hand, and overs remaining, what percentage of historical matches with that exact game state have been won by the batting team. And the platforms like CricViz have access to databases containing millions of T20 deliveries precisely to ensure this sample size, precisely to ensure this sample size. And the result is a model that can tell you in real time, after every single ball, the precise mathematical probability of each team winning. And it's not an estimate, it's the probability grounded in historical data. And now we are going to bring together everything we have learned till now, like Bernoulli trials, win probability, and delivery selection, and also run rate mathematics into a single case study here, the final over case study. This is the most high pressure scenario in T20 cricket. Like everything is distilled into 6 balls, like a over. The scenario here is 20 runs needed off 6 balls, and we have 2 wickets in hand, and the batter is a specialist slogger. Means he's a lower order batter who is not technically refined but has the physical power to hit sixes. The bowling team needs the wicket urgently but also cannot afford boundaries. So let us go through this ball by ball, and what's the win probability evolve? In the ball one, they are in serious trouble, and the bowling team's first ball was perfect, and the bat it was just a dot ball, so the runs required remains same, and the delivery type is a Yorker, and the win probability is 22%. And on the second ball, it's a slow ball, and the outcome is 6, and the runs required is 14 of 4, and the win probability increases to 41% here. And on the third ball, the delivery type is a short pitch, and the outcome is 4, and the runs required increases to 10 of 3. And the win probability also increases by approximately 17%, 58% total. And for the fourth ball, it's a full toss, which is a blunder from the bowling team side. And the outcome is a 6, and the runs required is 4 of 2. And the winning probability increased almost 20% here. And for the fifth ball, it's a wide. So it's also a blunder from the bowling team side, and the runs required is still 3 of 2, and the winning probability is 83%. And on the last ball, the bowler bowled a pace plus swing combo, and the outcome is a 4, and the batting team have won. Um, okay, now let us see how the win probability improves ball by ball. Initially, it was 22%, and then it became 41, and then 58, and then 79, and then 83, and then 100%. Here, the steepest jumps from 22 to 41 and from 41 to 58 happened on balls 2 and 3, uh, which means where the two boundaries happened. That is all it took to take the steep jump. And a match that was mathematically in the bowling team's control at 22% became a match in the batting team's control at 58% after two boundaries. And this is the mathematical reality of T20 cricket. Like win probability can shift by 30 or 40 percentage points on a single delivery. And the bowler's delivery choice on each of those critical balls, the slower ball on ball two, the short pitch on ball three, was either correct or incorrect in a very precise analytical sense. Uh, Not just tactically, but analytically. Cricket analytics can tell you the optimal strategy. It cannot execute that strategy for you. The bowler still has to deliver the ball precisely. The captain still has to communicate clearly, and the fielders still have to position themselves quickly and correctly. Here, the data informs, but the players has to execute, and both are essential here. Yeah, and let us see the death over delivery analysis into a complete comparison table here, because this is one of the most practically useful data sets in T20 cricket analytics. Looking at the death over delivery comparison, data compiled from over 17 through over 20 across large T20 datasets. The Yorker generates a dot ball of 58% of the time. It is the highest of any delivery type. It takes a wicket 9 9.1% of the time, and it concedes an average of 4.2 runs per delivery, and it results in a boundary only 11% of the time. It is the best executed Yorker in cricket is perhaps the single most valuable individual delivery in T20 cricket for a bowling team, because it combines high dot ball probability, low boundary risk, and reasonable wicket probability simultaneously. And then the slower ball generates a dot ball 41% of the time, which is significantly lower than the Yorker, but it takes a wicket 13.4% of the time, which is the highest wicket taking probability of any delivery type in this dataset. It consists a average of 6.8 runs per delivery, and it results in a boundary 22% of the time. The slower ball is the highest risk, highest wicket reward delivery in the death overs. The short pitch delivery and the bouncer or back of a length ball generates a dot ball 34% of the time, and the wicket taking probability is 11.2%. Average runs considered 7.1, boundary percentage 26%. Short pitch balls carry significant risk, particularly against confident batters who have strong pull shots. And the full toss is essentially the worst delivery you can bowl in the death overs on every metric. Only 12% dot ball rate, 5.8% wicket probability, the lowest of all five types listed. 9.4 runs considered on average. It's the highest, and 48% boundary rate. Nearly half of all full tosses in the death result in boundaries. And so a full toss in the death is effectively a gift to the batting team. It almost never happens intentionally, but it happens very frequently when bowlers mistime or misjudge their execution under pressure. And the bouncer. It is bowled significantly short and aimed at the batter's head or shoulder. It generates a dot ball 38% of the time, 10.6% wicket probability, 5.9 runs considered, 19% boundary rate, and the bouncer is interesting because it sits between the Yorker and the slower ball in terms of risk and reward. It disrupts rhythm of the batter, forces the batter to adjust their body shape, and can generate mishits. But against a batter who is set and confident, a poor bouncer can be pulled or hooked for six. And now let us bring all of this together into what we call the risk reward matrix for death over bowling. Here, the first situation is you need two wickets, and the batting team needs only 8 runs of the remaining six balls. What do you bowl? Of course, the slower ball. Why? Because you need wickets urgently. Wicket probability is 13.4% higher than any other delivery. But yes, it is more expensive if it goes for runs, but you need a wicket more than you need to save 4 runs. The slower ball maximizes your wicket probability at the cost of boundary risk. And this second situation here is you need to defend 4 runs in the last over. So no matter what happens, if you concede more than 4 runs, you lose. So what do you bowl? Of course, the Yorker, because every single ball, if you can exceed, because the Yorker has the lowest boundary rate at 11% and the highest dot ball rate at 58% and the lowest average runs considered at 4.2. So as your priority is containment, the Yorker is the best choice here. And the third situation here is uh, you are facing a dangerous set batsman who is in full flow. So because means he has been batting for 14 overs and is timing the ball perfectly. Every ball is going to the boundary. So what do you bowl? Of course, the bouncer. Why? Because to disrupt his rhythm, to force him out of his natural hitting arc, to change the length and pace and trajectory he has been calibrated to for the last 14 overs. A bouncer does not necessarily take a wicket, but it can break concentration, induce a top edge, or simply reset the batter's mental state. And the final situation here is uh, there is a tailender at crease. Uh, a tailender is genuinely number 10 or 11 who comes in at number 10 or 11. He's someone who can barely hold a bat. So what do you bowl? Death over situation. The data tells you the probability of each possible outcome for each delivery type. The bowler's job and the captain's job is to identify which delivery type maximizes the probability of the outcome their team needs in this specific situation at that specific moment against this specific batter. Data provides only the probability distribution. Player still has to execute the chosen option, and the analytical framework makes the decision rational and evidence based rather than instinctive. And this is the entire value proposition of death over analytics in a single sentence. And everything we have discussed so far, the short distribution maps, the bowler selection matrix, the conditional probability matchup tables, the win probability curves, all of it depends on one thing, the ability to collect, store, process, and analyze enormous volumes of cricket data. And that ability depends on a digital toolkit that has been built up over the past 2 decades and is now extraordinarily sophisticated. The first tool is the Python and R programming languages. We have the libraries in Python like pandas for data manipulation and NumPy for numerical computing and scikit-learn for machine learning, data wrangling, and regression models and player clustering. And SQL databases to store ball by ball records. It is also used to query millions of deliveries in milliseconds. And Table AU and Power BI. Uh, these tools are used to create interactive dashboards for coaches, live match visualization, and heat maps. And machine learning models, machine learning models like random forest and uh, XGBoost, which is also called extreme gradient boosting, uh, has transformed the predictive power of cricket analytics. Here, random forest is an ensemble learning method that works by building a large number of individual decision trees, each tree making a prediction based on a random subset of the available features, and then aggregating all those individual predictions into a final output. And the XGBoost, which is also called extreme gradient boosting, is a more sophisticated and computationally efficient variant that builds trees sequentially, with each new tree specifically designed to correct the errors of the previous trees. It is currently one of the most powerful predictive modeling algorithms available, and it has an accuracy of more than 82% in IPL matches outcomes. And then the computer vision. It is perhaps the most visually striking technology in the modern cricket analytics toolkit. Systems like Hakai use multiple high-speed cameras, typically 6 to 8 cameras positioned at different angles around the ground, to track the ball from the moment it leaves the bowler's hand. And ClickViz and Opta. ClickViz and Opta are the professional platforms that package all of these analytical capabilities into subscription services available to teams, broadcasters, and media organizations. ClickViz, in particular, has become the dominant provider of real-time cricket analytics globally. They also maintain a comprehensive ball-by-ball databases going back years, run live win probability models during matches, and produce the kind of detailed matchup analysis we have been discussing throughout this presentation. Uh, Many teams subscribe to these platforms and get access to both the historical analytical databases and real-time analytical feeds during matches. Like a quick quiz analyst embedded with the team can pull up the full bowler batter matchup matrix for any combination in seconds. They can show the captain precisely how a specific batter has performed against a specific bowler type across every match in the past 3 years. And they can do it in the in 30 to 40 seconds between deliveries. And the next topic is Duckworth Lewis turn method, which is popularly called as the DLS method. Every time rain interrupts a cricket match, DLS comes into play. It governs how targets are adjusted when overs are lost. And while virtually every cricket fan knows it exists, very few understand how it actually works. The DLS method was actually introduced in the international cricket in 1997. Its first use in international cricket was in Zimbabwe versus England ODI. It was developed by two English statisticians, Duckworth, Frank Duckworth, and Tony Lewis, as a mathematically sound replacement for various methods that had been used previously to adjust rain-affected match targets. Later in 2014, an Australian statistician called Stephen Stearns updated and recalibrated the method, particularly to improve its accuracy for T20 cricket. And the S in here, DLS method, stands for his name. The resource tables that underpin the entire DLS system contains only 550 individuals for ODI, and for T20 it's less than that. Each cell in the table represents a specific combination of overs. This is the table I mean mentioning, and each cell represents a specific combination of overs remaining and wickets lost, and gives the percentage of a team's total scoring resources that remain in that state. Like it's just like a Z table in statistics, which maps Z scores to cumulative probabilities. Like that, the DLS maps match states to resource percentages. It is a pre-computed lookup table derived from extensive statistical analysis of historical cricket data. And the fundamental target adjustment formula here is the target equals team 1 score multiplied by team 2 score, team two's resources divided by team one's resources. Mm, The core idea of DLS is that a team's ability to score runs, their run scoring potential, is a function of two resources, the overs available and wickets in hand. The more overs you have, the more time you have to score, and the more wickets you have, the more freely you can bat without fear of running out of batting partners. And if you lose overs to rain, you lose resources. And if you lose wickets in the course of play, you lose resources. If rain reduces team two's available resources, they should not be asked to score as many runs as team one, who had full resources. But they should still be asked to score proportionally to how much of team one's resources they have available. Now, let us look at the DLS resource table to understand how percentages are determined. Like if the batting team has 20 overs available and they played with full resources, means if they have 20 overs and they didn't lose any wicket, means they have 100% resources. And if they have 15 overs, means 5 overs is lost to rain, means they have 15 overs, and if they lose some around 4 wickets before rain, means 15 and 4, then their resources is 66.4%. So similarly, they use the DLS table here to calculate the resources and target after rain. And let us see a worked example here. Consider this match setup. Initially, the team one scores 185 in 20 overs, and the team two begins chase, and the rain interrupted at the end of 10th over, and the team two score at before the rain interruption is 88 with 2 wickets lost, and the overs lost to rain is 5 overs here. So the team two now faces 15 overs instead of 20 overs. So how much target will they have to face using DLS method? So the step one here is we need to calculate team one's resources here. So the team one had full resources, means they had 20 full overs and 10 wickets. So from this table, we can see they had 100% resources. And then the step two, we have to calculate team two's resources. They started with 100% resources, but they lost 5 overs due to rain. So from team two, from this table, we can see the overs available is 15 and the wickets lost is 2. So the team two's resources is 75.3%. So team two's resources is 75.3%. And let's apply the DLS formula here. So target is equal to team one score scaled by the ratio of team two's resources divided by team one's resources. Here team one score is 185 and team two's resources is 75.3 and team one's resource is 100. So the target is 185 multiplied by 0.753. So the DLS target is 140 or 15 overs. So the team two was initially chasing 185, but after rain, they need to chase 140 or 15 overs instead. So the new required run rate is 9.33, which is when compared to the original required run rate 9.25, it's just barely changed. means the DLS method worked perfectly here. Uh, Despite its mathematical sophistication, DLS remains one of the most debated topics in cricket, and engaging seriously with that debate reveals important truths about the nature of statistical modeling and its relationship to real-world complexity. There are three perspectives on the DLS method. The first one is the pro DLS, means they are the supporters of DLS. The pro DLS argues that it mathematically accounts for overs and wickets lost, which is more complete than old average run rate method. And the second perspective is the anti-DLS. They argue that it doesn't count for pitch deterioration, dew factor, or batting conditions in second innings. Means a momentum shift. And the analyst view, this is the true view I consider because it argues that DLS is the best model available, but is built on historical averages. But also outlier match conditions will always expose its limit. This is the limitation of any statistical model. So DLS is the best model available right now because the old models like average run rate method consider every over equally, even though if it's a power play over or a death over, it consider equally. So the DLS is the best method available right now. And here is a small question. Uh, Initially, team one scores 170, and the rain reduces team's two's innings to 15 overs. Team 2 has 75.3% resources. What is the DLS target? It's same as the previous question we just saw. Instead of 185, here it's 170. So the team 1 score is 170 multiplied by the team two's resources is 75.3 percentage divided by team 1 resources is 100 because they didn't lose any overs or wickets to rain. And so the final target is 128 approximately. And player clustering and auction strategy. Uh, we'll use k-means clustering to group players by multidimensional performance vectors. Here, k-means is an unsupervised learning machine learning algorithm. Uh, in supervised learning, you give the algorithm labeled examples, you show it data points and tell it which category each one belongs to, and the algorithm learns to classify new data points based on those examples. But in unsupervised learning, you give the algorithm data points with no labels, no predetermined categories, and ask it to find natural groupings or structure in the data on its own. K-means specifically works like this. Uh, you specify K, which is a number of clusters you want the algorithm to find. Say you want 4 player clusters. The algorithm randomly places 4 cluster centers somewhere in the data space. Then it assigns each player to the nearest cluster center. Then it recalculates each cluster center as the average position of all players assigned to it. Then it reassigns players based on the new cluster centers. It repeats this process, reassign, recalculate until the assignments stop changing. At that point, the algorithm has found stable, naturally occurring groupings in the table. Applying this to cricket, the data points are players here. The dimensions of the data space are performance metrics: batting average, strike rate, boundary frequency, dot ball survival rate, bowling economy, if applicable, and wicket frequency, fielding contribution. Each player is a point in the multidimensional performance space, and K-means finds which player players are naturally clustered together based on the similarity of their overall performance profiles. The four clusters that emerge from this analysis correspond to four distinct player types. The cluster A, they are the anchors. These players with high batting averages, typically above 45 or 50, but moderate strike rates. They are cricket specialists or ODI players. They are the batters who build an inning carefully and deliberately. They absorb pressure and they do not give their wickets away easily. And in T20 cricket, they provide stability at the top of the order during the power play and early middle overs. And then the cluster B, the finishers. They are players with lower batting averages, often below 30, but they have explosive strike rates, typically above 155 or 160. They are the death over specialists, and they do not bat for long in terms of ball space. They get out frequently, but uh, when they are at the crease, they score at a rate that can change a match in 4 or 5 overs. And then the cluster C, the openers. They are players who combine a genuinely strong batting average with a strong strike rate. They are power play maximizers. They have the defensive technique to survive the new ball, good footwork, solid defense, ability to leave deliveries outside off stump, combined with aggressive intent and shot making ability. And then the cluster D. They are the all-rounders. These are the analytically most interesting players because they resist easy categorization along any dimensions. Their batting average is decent but not exceptional. Their strike rate is also good but not explosive as finishers. But they also contribute significantly with the ball. Reasonable economy rate, genuine wicket taking ability. Uh, and the reason all-rounders command premium auction prices is precisely because they fill two roles simultaneously. In a squad of 15 or 20, having players who can bat at 5 and also bowl 4 tight overs is enormously valuable from a tactical flexibility perspective. And here is what where the auction strategy application becomes really powerful. In an IPL auction or any franchise cricket auction, teams have a fixed budget. Every decision about how much to bid for one player is a decision to have less money available for every other player. The analytical challenge is to build a optimal 11 maximizing collective performance across all phases of the game and all aspects of cricket within a budget constraint. Here, K-means clustering helps teams solve this problem systematically. First, the team identifies which cluster they are short of. Do they have plenty of anchors and openers but lack an elite finisher? They need to target cluster B players in the auction. Second, within their target cluster, the team uses Z-score to identify which players are undervalued by the market. The player whose Z-score on relevant metrics places them significantly above the cluster average, meaning they are objectively performing better than most players in their type. But who is being priced below the cluster average in the auction represents genuine value. And this is exactly the Rajasthan Royals model from 2008 that we discussed in the first section of this presentation. Uh, they identify players whose true performance measured by a comprehensive multimetric Z scores significantly exceeds their auction price. And they bid strategically for those players, build a team of high performing but underpriced players. They won matches through roster quality that exceeds their budget allocation. Um, the combination of these analytically identified undervalued players assembled on a tight budget produced an IPL champion in 2008. And the analytical framework that explains why it worked is K-means clustering combined with the Z-score analysis, just as we described. And one small question for you guys. A player has a strike rate of 175 and a batting average of 22. Using the k-means clustering model, which cluster does this player belong to? The first option is cluster A, anchor. The second option is cluster C, opener, and the third option is cluster B, finisher, and the fourth option is cluster D, all-rounder. In which cluster should this player belong to? Yeah, he's a finisher because he has an explosive strike rate of 175 and he has a very less batting average of 22. And let us close this out with five core principles. Think of these as the five things you should walk away remembering from everything we have covered today. The first one is every ball is a data point. Cricket analytics starts at the most granular level possible. Every single delivery is recorded with multiple variables like outcome, speed, line, length, batter position, shot type. This ball by ball data is the foundation of everything we discussed. Without it, none of the metrics, maps, or probability curves are possible. And the second one, metrics beat intuition. The Z score, the batting average, the strike rate, the economy rate, the dot ball priority. Each of these replaces a vague gut feeling with a precise, quantifiable, comparable number. Intuition has its place, but metrics built from thousands of data points are more reliable and more consistent. And the third one, probability drives strategy. The matchup matrix, the win probability curve, the required run rate delta, the DLS resource table, all of these replace imprecise judgments about match situations with concrete probabilistic estimates. And a captain using these tools is not guessing. He is working with the best available information. And the fourth one, machine learning is not the future, it is the present. Clustering, computer vision, Bayesian models, random forest algorithms, these are already deployed in professional cricket right now. Teams not engaging with these tools are competing against opponents who have a significant information advantage. And fifth, data plus domain knowledge. The powerful analyst combines statistical rigor with deep cricketing understanding. And the data tells you what domain knowledge tells you why. And you need both data and domain knowledge. So, thank you guys.
Guys, the attendance link is in the chat. You can fill the attendance form and leave. Thank you.